Hello everyone. In this brief video, we are going to talk about elements of GD&T. So there are 6 elements that we have to briefly mention: datum reference frame, datum feature, basic dimension, feature control frame or FCF, and then GD&T symbols. And for GD&T symbols, I am going to go over a separate video and talk about the meaning of each one of the symbols. So if we want to talk about the datum reference frame, it's basically a coordinate system like a Cartesian, preferably a Cartesian coordinate system that we use to describe the motions of the part with respect to, like here, for example, translation along x-axis, along y-axis, along z-axis, and then the rotations about these 3 axes, so 6 degrees of freedom. And when we want to inspect the part, we have to basically take this 6 degrees of freedom away from the part and make the part completely fixed so we can do our inspection. Okay, if the part can freely move along any of these axes or rotate or anything, then we cannot do accurate measurements. So this is our reference frame. The datum itself is a theoretical axis, plane, or point. It's a theoretical feature, really, not a real one. So that you use to establish the datum reference frame. So for example, here I can say I can use this edge here on the back, this edge here, and this edge here, and then using these 3 edges as my datums, or you might call data, really, right? Sum of datum is data, I assume. Then you can establish a coordinate frame. So the thing is, that edge here, this edge and this edge, they are theoretical. They are something I can see in a CAD model. In real world, when I manufacture the part and I have the real part, then the corresponding physical features for those edges, which are the physical real edges, those I call a datum feature. Or this back surface, or this bottom or top, or any of these other surfaces in the CAD model, the virtual one, theoretical one, I can call a datum. And then when I manufacture them, those actual faces or surfaces, I call them a datum feature. Well, what's the difference? The difference is these theoretical ones in the CAD model, or when you just imagine the part, these are perfect. There is no imperfection in them. Right? They are perfectly straight. There is nothing wrong with them. They are exactly the way they are supposed to be, right? If it's a flat surface. And in reality, that's not the case. Everything we have in reality, it has some imperfections. So your datums, the datum features, the physical datums, they are going to be what? Not 100% perfect, and we'll get to that. So that's the difference between a physical or a datum feature and the theoretical or pure datum that we use in a CAD model. We show datums using a square, and then we attach this square to a triangle, and then we attach the triangle to that datum, right? So here, if I want to refer to this bottom edge or the bottom surface, then I attach it to a small triangle and then attach the triangle to the square, and then each datum has a name. Typically we use letters like A, B, C, and these are the sizes for a datum feature, which a CAD software will automatically give you those, so we don't need to really worry about any part of that. The important thing about datum is the order of them matters. Most of the time you have more than one datum. You have several datums, like you can see here. So, and the order matters. So if I want to control the location of the center of this hole here, right? And we'll get to that in the next video and a little bit in this video. The order of these datums is important. So when I want to take those 6 degrees of freedom away from the part, in which order do I start laying those datum features against the surfaces that I have for my control table. And in that order, as we go from left to right, the final position that we are measuring for the center of this hole, let's say, is going to be completely different. So let's say the part that I want is not going to be perfectly manufactured as a square. There is some imperfection here, or maybe the part itself is what? It's just made like a trapezoid, and I have a pattern of this circular holes, 4 of them on it, right? And I want to measure the locations, right, of the hole or anything for that matter. So I want to control any tolerance. Now the thing is, if my surface A is, let's say, the top or the bottom surface, so let's say it's the bottom surface, for example, I lay it on the table. So this is a top view right now. You're looking at it from the top. I put the bottom surface at the table, so I assume that the top surface of the table is perfect, good. I put surface A on it, laid on the table. Now, these are the 2 vertical walls on that table, these 2 gray walls. If I first fix B, which is this edge here, and then C, right? Well, here, because of the imperfection, there is no way that I can, when I lay B, there is no way that I can lay this surface here against C. Sorry. There is no way that I can do that because this angle is not 90 degrees, okay? So when I fix B, that's all I have. I cannot go with C. And now I can look at this whole position and then the deviated version of that and see if it's made correct or not or anything. But if I say ACB, I reverse the order and say C first, then B. So here you have to first lay this basically edge here against this right wall, and then you cannot make B against this bottom one perfectly. There is no way, again, because this angle is not 90 degrees. And so now the hole is completely in a different position. You see this one with respect to what? This one. And so the measurements and the positions of the center of the hole and everything will be affected as a result. The next thing we have to discuss is basic dimensions. So basic dimensions, I mentioned them in a separate video under SolidWorks playlist, I assume. But basic dimensions are the dimensions that you use them most of the time for true positions and with patterns and so on. And they don't have a tolerance on their own. Okay, as you can see, there is no tolerance box, no FCF with them, feature control frame. And they are used to show the true or the theoretical location of something. Okay, so if I have this hole figured out, the center of that, this guy is exactly 2.2 units to the left, no upward, downward, and this one is, once I figured this one, this is exactly 1.2 units above that, no left or right. So these are theoretical perfect locations, and then you might say, what if basically we want to show tolerance for those dimensions? Well, for those dimensions, the inaccuracies, they are described by the initial position of what? The first center by this FCF. So I talked about this basic dimensions in a separate video, and my goal is not really to go more into that, but we have basic dimensions, we have datum reference feature, and we have feature control frame, or FCF, which is how you show a geometric tolerance. So geometric tolerance, unlike the linear tolerance that is like a plus and minus some number, geometric tolerance is always shown using this box that you attach to the portion of the part that you want to control and you want to inspect, and it has several parts. The right part of it is the part for the datums, and again the order matters from left to right. The left side of it is the symbol of the geometric tolerance, the thing that you're trying to control. And then inside the middle part, typically the most important thing is this number, which we call the tolerance zone. And then there might be some other symbols. This phi is not typically something you always see. The most important thing after the tolerance zone are modifiers, right? M and which is for maximum material condition, and as we'll see, we have the least material condition, right? So this is for MMC and then LMC, right? So you have M and L. So we have these modifiers, and we'll get to the modifiers. So again, in the middle box, tolerance zone modifier. On the left side, the symbols. On the right-hand side are the datums in order of which one to start fixing first. The final thing we have are GD&T symbols, which there are 5 categories in general, or 4 categories, I would say, plus the modifiers. So the modifiers are M and L, which we're going to talk about them in a separate video. But the 4 major things we have in general are form, position, orientation, and what? Runout and profile. So forms are straightness, flatness, circularity, and cylindricity. Position is the true position, concentricity, and symmetry. Orientation is angularity, perpendicularity, parallelism. Runout is the circular and total runout, and profile is the profile of a line and profile of what? A surface. So in my next video, I'm going to talk about the meaning of all of these symbols. And in the next video after that, I'm going to talk about the material modifiers. So in 2 separate videos, I'm going to talk about the meaning of them, and I show you different sorts of examples, and you'll see how to understand and interpret these different GD&T feature control frames, basically. So thank you for your attention, and I'll see you in my next video.